The new chapter which we are going to discuss today is about complex numbers. We have discussed randomly about the complex numbers in the number system, as we have seen that there were different set of numbers which have come initially with the natural numbers and then the whole numbers and then the integers and then the rational numbers and then the real numbers and finally with the complex numbers. So when it comes to complex numbers, we have identified that they are the highest numbers, or all the numbers which you are discussing here are included in complex numbers. Now let's discuss about additive identity, where the biggest question comes: what if I take the complex number z1 is ab and my second complex number as 0, 0? Does this belong to the complex numbers? And yes, because in this case both of them belong to C, since a comma b belong to R, and 0 is always a real number which belongs to the real numbers, and hence this belongs to the complex number. So this 0, 0, which is origin, also belongs to the complex numbers. Now using this, if I want to find z1 plus z2, let's see what is the outcome. Interestingly, if I substitute this for AB and z2 with 0, 0, this is addition of two complex numbers, which is respectively addition of their respective terms. Therefore, this is a plus 0 and b plus 0, which on further simplification gives a plus 0 is a and b plus 0 is b, is what I get. But AB is nothing but z1. So therefore, I get z1 plus z2 is, again coming back to z1, again I get even z2 plus z1 is z1. This shows that when z1 yields back, when z2 yields back the z1 back again, that means this particular property, this particular element is called additive identity. That implies z1 equal to 0 is called the additive identity in complex numbers, is how we identify the additive identity. So 0, 0 is called additive identity in complex number because it generates back the element. Oh, this is z1 plus z2 gives back z1. So z2, I'm sorry, this z2 equal to 0 is the generating back z1. Therefore, this complex number z2 is called the additive identity in C because it generates back the element z1. Even here, it generates back the element z1. So z2 equal to 0, 0 is called the additive identity in complex numbers. Now let's see the additive inverse. Say for example, I take a complex number z equal to ab belonging to C, that implies a comma b belong to R. Then I know that respectively the complex number z2, which is 0, 0, also belongs to complex number, since 0 belongs to R. And then this is called the additive identity, as we discussed in the previous session. Now z1 equal to a comma b implies, say z3 will be minus z1, that is minus of a comma b, which is minus a minus b, which belongs to C, since minus a and minus b belong to R. Now the reason why I have taken the term minus z1 is I want to find the additive inverse of z1. Therefore, if I take z1 plus the something, I need to get back 0, 0. So what is the element I need to fit in here that I get back 0, 0 is what is called additive inverse. So clearly I see that z1 being a comma b, then if this is filled with minus a comma minus b, then obviously I get this equal to 0. Let's see, because when I substitute for z1, this is a comma b plus minus a minus b, which we are going to prove for 0, 0. That is, when I take this a plus minus a, b plus minus b equals 0, 0. And then a minus a or a plus minus a is 0 in real number system, and this will be 0 is exactly identical to be 0, since I have a plus minus a equal to minus a plus a equal to 0 in the real numbers. In all real number system we have this, and therefore this is identically equal to this. That implies the element which is generating identity, additive identity, is called the additive inverse of Z1. So that implies Z3 equal to minus Z1, or this equal to minus A minus B, is called the additive inverse of Z1 equal to AB and vice versa. That is, Z1 is called the additive inverse of Z3 and Z3 is called the additive inverse of Z1, is how we understand the additive inverse of AB is minus A minus B as identified here, and additive inverse of minus A minus B is instead AB as identified under the additive identity 0, 0, is how we understand this. Now let's see the commutative property. As we know that commutative property is when I reverse a plus b and b plus a, they must be equal. So therefore equally, if I have two complex numbers, z1 equals a1 b1 and z2 equals a2 b2 belonging to the complex number, that implies a1 b1 a2 b2 belong to real numbers by definition of complex numbers. Now for commutative property, my z1 plus z2 is a1 b1 plus a2 b2, which on addition of complex numbers gives me a1 plus a2 and b1 plus b2, which is clearly by the addition of complex numbers. Now as I know that these two are real numbers, I can interchange them because the real numbers have the freedom of changing, because r plus is commutative, and therefore this reduces to a2 plus a1 b2 plus b1 when interchanged, because r plus is commutative, is what we get the property. Now again, splitting back the addition of two complex numbers, I split back to get a2 b2 plus a1 b1, which comes by definition of addition of complex numbers. Therefore this being z2 plus z1, therefore I identify that z1 plus z2 is this. That implies C plus holds commutative property, is how I conclude with the supporting proof. So the set of complex numbers under addition holds commutative property because this plus this is equal to this plus this for any two complex numbers in the complex number system. Now next is associative property under addition. So in this case we take the three complex numbers, but as we know that since the set of real numbers under addition is associative, therefore obviously the real numbers included in complex numbers is also associative or holds associative property. So we need not do much on, because when I take three real numbers a, b, c, or a1, a2, a3 and b1, b2, so therefore with these three complex numbers z1, z2, z3, I clearly have z1 plus z2 plus z3 is obviously z1 plus z2 plus z3 for all complex numbers z1, z2 and z3. Associative property holds very much in case of complex numbers, is how we understand under addition. Now let's see the multiplication of two complex numbers before we understand the various properties which hold for the complex numbers under multiplication. How do we multiply the two complex numbers is the biggest question here. Say for example, I take the first complex number a and b and my second complex number C and D, then clearly I know that this can be written as A plus IB and this as C plus ID, where each of this belong to C and A, B, C, D belong to the real numbers, is how I understand the basic definition of complex numbers. Now that we have Z1 and Z2, I want to find the multiplication of Z1 and Z2 as the product. So therefore, when I take the product Z1 into Z2, the multiplication as denoted with this, then this is clearly AB dot of CD, is how I understand the multiplication of two complex numbers. Now the complex number AB, which is generally denoted with other form as A plus IB, can be written for A plus IB for the first term and then multiplied with CD, which can be written as C plus ID. Now I want to expand the entire brackets where the ordered pairs are converted into the addition, and then when I expand this, A multiplied with this AC plus AD times I plus BC times I plus I square of BD is what I get. Now since I is root minus 1, that implies I square is minus 1 is what we get, through which I substitute for I square equal to minus 1. Therefore, AC plus this with I taken common, I get AD plus BC, and this I square being minus 1, I substitute this for minus BD is what I get. Therefore, taking all the real parts, AC minus BD plus I times AD plus BC is what I get when I take the product of two complex numbers, this. Or this can also be written as AC minus BD, comma AD plus BC is how I understand the product of two complex numbers written in this form or this form. And clearly this is a complex number because each of them is a real number, as can be clearly seen. Each of them is real number, and how the multiplication of two complex numbers is defined as AC minus BD, comma AD plus BC. Now let's see the closure, associative, commutative, identity, inverse properties involved with multiplication. So initially, to start with, closure property, it clearly says that Z1 and Z2 belonging to complex numbers implies Z1 dot Z2 is also a complex number. And that is, the closure property holds under multiplication. Therefore, the property says that this implies this for all Z1 and Z2 belonging to Z. C, Z1 dot Z2 also belongs to C. The second is associative property. Associative property, through which I get for all Z1, Z2 and Z3 belonging to C, that implies Z1 dot Z2 times Z3 will always be equal to Z1 times Z2 times Z3 for all of each Z1, Z2, Z3 belonging to C. So commutative the associative property also holds under multiplication is what we identify here. The next is commutative property, which says that for all Z1, Z2 belonging to C, that implies Z1 into Z2 is always equal to Z2 times Z1. So even commutative property holds under multiplication of complex numbers. Then the next is existence of identity. So in case of identity, we have identified that additive identity is 0, 0, but here the multiplicative identity is what we are going to discuss in this case. So when I have Z1 equals A, B belonging to C, and my identity Z2, let me denote the multiplicative identity with I, which is 1, 0, which also belongs to C, since 1 and 0 are real numbers. So let's see if this when multiplied with this gives back the term a comma b, is how we identify the properties. So in this case, when I multiply the identity 1 comma 0 here, I get that z1 times of I, which is a comma b times of 1 comma 0, which on multiplication gives me ac minus bd, that is a times of 1 minus b times of 0, and ad plus bc, that is a times of 0 plus b times of 1, is what I get when I use the multiplication property of multiplying the two complex numbers, ac minus bd, ad plus bc, which gives me a comma b on simplification, which is nothing but z1. Therefore, my z1 times of I, which is z1, is I times of z1, is what gives me the identity property. That implies I equal to 1 comma 0 is the multiplicative identity in the set of complex numbers under multiplication. So I identify that 1 comma 0 is the multiplicative identity in the set of complex numbers under multiplication, because this complex number generates back z1. That is, when I multiply I to z1, I get back z1. So this property shows that this is the multiplicative identity of a complex number under C dot. Now let's see what is the multiplicative inverse of a complex number, or how the properties hold when I take into consideration the multiplicative inverse. As we have seen with the additive inverse, we have seen that minus z1 is the additive inverse of z1, is how we see the similar property under multiplication. Now that, let me take a complex number z1 equals a comma b belonging to the complex number, and I have identified the identity as 1 0 belonging to C is the multiplicative identity, as we have seen in the recent session. Now that we have identified that 1 comma 0 is the multiplicative identity, then the question comes that for inverse to exist, when z1 is multiplied with something, I must get back I. Then let's see what is to be multiplied to this to get back I, is the biggest question. Now because I don't know that what should be here, I take this as x comma y, because I don't know what exactly is to be filled in. I take x comma y here. Then let's see what will be the value of x and y I obtain in terms of a, b, 1 and 0. So my z1 being a comma b is substituted here with dot of x comma y equals I, which is 1 comma 0. That implies the multiplication of two complex numbers is clearly defined. ab dot xy is 1 0, for which I am going to multiply the two complex numbers. So the multiplication of complex numbers in this case is ac minus bd. So this into this minus this into this gives me ax minus by, and ad plus bc, which gives me ad plus bc on the whole, which is 1 comma 0. Therefore, when two of the complex numbers are equal, then each of them are respectively equal. That implies I get ax minus by equal to 1 and ay plus bx equal to 0 is what I get here. Now I want to find x. So in this case, I multiply with b, and then this I multiply with a, so that my modified equations will be abx minus b square y equal to b, and then in this case abx plus a square y equal to 0 is what we get, which on simplification through subtraction gets minus of a square plus b square of y equal to b. That implies my y is equal to minus b by a square plus b square, which on substitution in one of the equation gives me the x. That is, when I substitute this in the equation ay plus bx equal to 0, substitution in this implies a times of y plus bx equals 0, that implies bx is ab by a squared plus b squared. Assuming that b is not equal to 0, I have this x equals this equal to this. Then this will be a by a squared plus b squared. And my y equal to this and my x equal to this defines the multiplicative inverse. Therefore, multiplicative inverse of AB, Z1 equal to AB, is a by a squared plus b squared and minus b by a squared plus b squared is how we understand the multiplicative inverse of a and b is given to be a by this minus b by this is how. And since this clearly belongs to complex number because each of them is a real number for all a, b belonging to R. So multiplicative inverse exists and it is this for a comma b is how we understand. So next is the distributive property, which is combination of both addition and multiplication. Say for example, the distributive property says that if I have z1 dot times z2 plus z3, then in that case this is z1 dot z2 plus z1 dot z3 is how I identify the distributive property under addition and multiplication. So this very much holds in case of complex numbers, as can be proved with various examples. So distributive properties hold very much in the set of complex numbers. Now the multiplicative inverse, which we have already discussed in case of complex numbers, we will try to solve some problems using the multiplicative inverse property. So to revisit the multiplicative inverse, if my complex number z1 or z is a comma b, then we have studied that its multiplicative inverse denoted by z inverse is given by the formula a by a squared plus b squared. So we have seen that if I take the complex number z equal to ab, then z inverse is a by a squared minus a, it is a by a squared plus b squared and minus b by a squared plus b squared is how we have the formula. So with this, if suppose for example I wanted to find the multiplicative inverse of say z is 7 plus 24i and I wanted to find z inverse is the question out here, then how do I find multiplicative inverse or z inverse? So to find the multiplicative inverse, I simply try to take this denominator with a squared plus b squared is which is common outside. Therefore my a is 7 and my b is 24. Therefore z inverse is 1 by a squared plus b squared of a, which is 7, and minus b, which is minus 24. This is strictly using this formula. So using this formula, I get this to be this, where a squared plus b squared is common, so I have taken out on the whole. So this now reduces to 1 by 7 squared, which is 49, and 24 squared, which is 576 of 7 and minus 24. This on further simplification gives 1 by 625 times 7 and minus, which on finally reduces to 7 by 625 and minus 24 by 625 is how the z inverse is obtained. That is, I understand the multiplicative inverse of this is 7 by 625 plus or minus I times 24 by 625 is how I understand the complex number, which is the multiplicative inverse of 724. So therefore multiplicative inverse of 7 plus 24i is 7 by 625 or minus 24i by 625 is how I understand the multiplicative inverse of a complex number. Now, division of complex numbers. Now that we have discussed about addition, subtraction and multiplication of complex numbers with their inverses and identities, now next comes on identifying the division of complex numbers. Of course, division of complex numbers has its own limitations, because if we have a zero complex number cannot be divided. Therefore, the restriction is that in division the denominator is assumed to be non-zero complex number. So for a non-zero complex number existing in the denominator, if I wanted to divide two complex numbers, say a plus ib and c plus id, that is, if I take in the form ab over cd, or this is z1 over z2 is how I take, where z1 is this and z2 is this, then in this case, how do I divide the two complex numbers? What will be this equal to is the biggest question out here. So let's see how the division process can be done for complex numbers. Say I take one example problem for which I wanted to find the division of 3 minus 4i by 4 plus 5i. So this is my complex number in division form, where the complex number in the numerator is 3 minus 4i and that in the denominator is 4 plus 5i. Now I would like to find the solution or simplify the division part to get a new complex number. So how do I divide the two complex numbers is the biggest challenge in this session. So as I observe here, the denominator is with complex number, so I try to use the concept of rationalizing, because if I don't want the I term in the denominator, I need to rationalize the denominator. It's just like removing the root. If I have a root in the denominator, I rationalize the denominator. So in the same way, to remove I just try to rationalize the denominator. Now rationalizing the denominator implies if I have 4 plus 5i in the denominator, I multiply and divide with minus term. If I have minus here, I multiply and divide with plus. That is, in this case, it is 4 plus 5i. So I multiply 4 minus 5i because the plus changes to minus in case of rationalizing. And then equally when I multiply, I also divide with 4 minus 5i in the denominator. This is called the rationalizing concept of plus with minus, or when minus with plus. So here, once I rationalize the denominator, let's see what comes in the next solution. 3 minus 4i into 4 minus 5i multiplied, taken in together. Now this is clearly a plus b into a minus b, which is a square minus b square. So a plus b times a minus b is a square minus b square on the whole. Next, I would like to simplify the numerator factors by expanding the brackets on the whole. So first 3 multiplied with this, 3 fours 12 minus 3 fives 15i minus 4 fours 16i plus 5 fours are 20 times I square is what I get in the numerator. And then this being 16 minus 25 I square is what I get in the denominator when this is expanded along whole square. Now as I know that I is the imaginary number, I is root of minus 1, then I square is minus 1 is how I understand I and I square. I is root minus 1, that implies I square is minus 1. Therefore in this case, when I simplify, 12 minus 15 plus 16i, that is minus 31i plus 20 times of I squared, which is minus 1. So in place of I squared, I substitute minus 1. And similarly, in the denominator, I have 16 minus 25i squared, which is minus 1, is substituted in place of I squared. So this, on further simplification, gives me 12 minus 20, and then in the denominator, it is 16 plus 25, which is 41. So this, when written in split form, minus 8 by 41 and plus I times of minus 31 by 41 is what we get when we expand this. That is, therefore, the division of the two complex numbers 3 minus 4i by 4 plus 5i is nothing but minus 8 by 41 plus I times minus 31 by 41, or I can write this as minus 8 by 41 and minus 31 by 41 is how I understand the division of two complex numbers taken in the rationalizing concept. Therefore, the division of this by this is this, using the process of division. Now next is integral power of a complex number. That is, what happens when I raise the complex number to some integral power. So let's see how the different properties are identified in case of integral power. That is, let z belong to a complex number and let z not equal to 0. That is 0 comma 0. So we are taking a non-zero complex number. And next, let n belong to the integers. These two, n being an integer and z being a non-zero complex number, we have the properties which say that the integral power of n, that is, when I raise the complex number to some power which is an integer, the integral power, then I have various properties here. Then z power n will be z if n is equal to 1, and this will be 1 0 if n is equal to 0, because when z power 0 is identity, and the identity in complex numbers, the multiplicative identity in complex numbers is 1 0, which we have already discussed in the previous session. Therefore, if n equal to 1, it is z, and if n equal to 0, this will be 1 0, and if n is greater than 0, I can write this as z power n minus 1 into z using the loss of index. And next, if n is less than 0, then I can write this as z inverse of minus n. So these are the various properties which we see in integral powers for each of n equal to 1, n equal to 0, n greater than 0, and n less than 0. So for each of the case where n is positive or negative or etc., we use this concepts. Say for example, if I just connect this with an example, if I take the complex number z is 3 plus 4i, then if I wanted to find first, say z power 1, now z power 1 is nothing but z, that is 3 4. So the power of 1 is assumed as the complex number itself. So z power 1 is z using the first property. If, for example, I wanted to find z power 0, then 3 plus 4i whole power 0 is always 1 0. That is, this will be 1 comma 0 is how we understand the second concept. Now thirdly, if I wanted to find, say, z square, then I just write this as z power 1 times of z power 1, because n minus 1 times z is 2 minus 1 times z, which is nothing but z power 1 times of z, which is z into z. Now z into z is nothing but 3 4 into 3 4, which we have seen as the product of two complex numbers AB dot CD is AC minus BD. So AC minus BD, that is 3 times of AC minus BD, and this is AD plus BC, that is AD plus BC is what we get using the multiplication of two complex numbers. This is 9 minus 16 and 12 plus 12, which comes out to be minus 7 and 24. Therefore, the square is minus 7 and 24 is how we understand the complex number through this. Now lastly, let's see what happens when n is less than 0. So lastly, we will try to find, say I want to find z power minus 2. Then how do I find z power minus 2? Because n is minus 2, n is less than 0. So I use the fourth case, which says that if suppose I wanted to find z power minus 2, that is 3/4 of minus 2, then I use this as z inverse of minus n is how I get, that is z inverse of minus n is 3/4 inverse of minus 2. That is, I can write this as minus 1 times 2, that is 3/4 inverse of square. That is, I first put minus and then 2 outside, because minus 2 can be written as minus 1 times of 2. It is just like using a power minus m is a inverse whole power m, is how I understand this concept. So this one, first I find inverse and then square of that inverse. So in this case, 3/4 inverse is directly found by using the inverse of complex numbers concept, that is 3 by 3 square plus 4 square, and minus 4 by 3 square plus 4 square, which we already seen in the inverse formula, a by a square plus b square minus b by a square plus b square, which comes out to be 3 by 25 minus 4 by 25. Therefore, if I wanted to find, substituting this here, I get this as, that implies z power minus 2 is 3/4 inverse is 1 by 25 of 3 minus 4 whole square. So when I do the square of this, I get this as 1 by 625 of 3 minus 4 whole square, which can be found using the product of two factors, that is 3 minus 4 times 3 minus 4, which can be done as AC minus BD. So this comes as 1 by 625 of 3 3s are 9. AC minus BD is AC minus BD, and AD plus BC, which is minus 12 is what I get as 1 by 625 times of minus 7 minus 24. So this is how we get z power minus 2. So z power minus 2 is 1 by 625 times minus 7 minus 24 is how we do for the last case. So each of the cases where n equal to 1, 0, greater than 0 and less than 0 have their own respective formulae through which the complex numbers can be operated. Now that we have seen a complex number which is constructed with real numbers connected with the complex roots, so let's see how we differentiate the real and imaginary parts of a complex number, because a complex number is said to have even a real number attached to it independently. To understand this more clearly, let's revisit the complex numbers definition which we have seen in the previous session. So if I take the set of complex numbers, I have this in the form a plus ib such that a and b belong to R, or also written in the form a comma b where a and b belong to R. So in this case, this is the representation for complex numbers. I see that as I take one of the complex number z as say x plus iy, then this complex number which belongs to C has two parts. One is this and one is this. So this is called the real part and this is called the imaginary part because this is associated with I. Because this is associated with I call this as imaginary part. Therefore, every complex number x plus iy has real part which I denote with Re of z. That is, when I say Re of z, it indicates the real part, and this is nothing but x in case of this problem. And the imaginary part I denote with Im of z, which is nothing but the imaginary part is y, is how I denote with this. So these are the basic formulae which I take in a complex number. The real part is the one which is not associated with I, and the imaginary part is the one which is associated with I. Say for example, I take 7 minus 4i, or say I take z is equal to 7 minus 4i. Then in this case, my real part of z is 7 because this is independent of I, and my imaginary part of z is minus 4 because coefficient of I is minus 4 is how I understand this concept of real and imaginary parts of a complex number. If suppose I have a complex number 23i, then in this case my real part is not existing, so this is in the form 0 plus 23i, that is, this is real part of z is 0 and imaginary part of z is 23, is how we understand the concept. So real part is 0 and imaginary part is 23 because there is no real term, only coefficient of I. So this gives rise to an interesting property that all real numbers are complex numbers whose imaginary part is 0. That is, all real numbers are complex numbers whose imaginary part is 0, is how I conclude. Because if I write in the form a plus ib, which is a plus I times of 0, then this is clearly a plus 0, that is a. It's strictly a real number, is how I understand the real number concept. With a plus ib is equal to a plus I times 0, that is a, which is a real number. So now that we have discussed already about conjugate of a complex number, let's see what are the various properties associated with conjugacy in extension. So let me take a complex number z equals a plus ib. That implies conjugate of z denoted by z bar is nothing but replacing I with minus I. Wherever there is I replace with minus I, and hence I get a minus ib. Now in this case, the real part is a and the imaginary part is b, and in the conjugacy the real part is a and the imaginary part is minus b, is how we understand this. Now as I clearly see this, I see that when I add each of z plus z bar, I get a plus ib plus a minus ib, for this being this and this for z bar. Now these two being equal get cancelled and I get 2a. That implies a is z plus z bar by 2 when I bring 2 down. So a being the real part of z implies the real part of z is always z plus conjugate of z by 2, is how I take the standard formula for real part of z. So this is how we take the formula for real part of z is z plus z bar by 2. Similarly, when I take z minus z bar, then I have, let's see what happens when I take z minus z bar. Now z being a plus ib minus of a minus ib is what I get for z minus z bar. So on expansion, this leads to a plus ib minus a plus ib, which gets cancelled. So this on simplification gives 2ib is z minus z bar, that implies b is z minus z bar by 2a. So b being the imaginary part of z, of this z, real part is a and imaginary part is b. So the formula says that imaginary part of z is z minus z bar by 2i, is how we understand the real part and imaginary part of z, which are constructed with these properties. Now every complex number is identified to be with I, so there are some extended properties which are connected with real numbers and I. So this topic is exclusively about standard representations of I. To revisit with a complex number defined with, say, if I take z belongs to C, can be written in the form a plus ib, such that a and b belong to R and z belongs to C, then in this case every complex number is defined in this. Then if I have a standard complex number, say 1 0, or say this is 1 comma 0, then this can be represented as 1 plus I times of 0, that is 1 plus 0, that is 1. So the real number 1 can be represented in the complex form as 1 comma 0, that is 1 0 is 1, is how I understand. That implies we understand this to be 1, is how we understand. Similarly, if I have 0 1, I can write this as 0 plus I times of 1, that is 1 can be written in this form as a plus ib, which comes as 0 plus I, which is I. That implies my 1 0 is 1 and 0 1 is understood as the imaginary number I. Similarly, if I just have say for example I have minus 1 0, then in that case this is nothing but minus 1 plus I times of 0, which is minus 1. That implies minus 1 0 is understood as minus 1. So like this, there are various properties through which finally I come with 0 minus 1, which can be written as I times minus 1, which is minus I. Therefore the property says 0 minus 1 is minus I. So these are 4 exclusive properties which are connected with the complex numbers. Basically, we need to understand that I is a complex number, which I is a root of the Euler's equation x squared plus 1 equal to 0, and the value of I is given as root of a negative number, or root minus 1, and I is this, or we can say I squared is minus 1, is how we understand I in its standard representation. So I is a root of the Euler's equation x squared plus 1 equal to 0, and I is root minus 1, or I squared equal to minus 1, is the defined complex number. So without I existing, we cannot say it's a complex number, but you can say it's a purely imaginary number. So therefore, in this case, this and this are complex, this and this are purely real, is how we understand. So let's see what do you mean by purely real and purely imaginary. To take a complex number, say for example z equals ab or a plus ib, then we say that a equal to 0 or b equal to 0 implies, if I take initially with b equal to 0, implies this reduces to z equals a comma 0, that is a plus I times of 0, that is a. Therefore, b equal to 0 implies z is purely real because this is a real number. So we say that the first part is purely real and the second one is purely imaginary. That means when the whole of b vanishes, then in that case z is called purely real, is how we understand this. Similarly, when a is 0, so let's see what happens for this a being e0, then z would be 0 comma b, such that this would be 0 plus ib, that is bi, for all b belonging to R. Now this is purely imaginary because there is no real part attached to it. Therefore, a equal to 0 implies z is said to be purely imaginary. That means there is only a term multiplied with I. There is no constant term identified out here. So this being the case. So these are the properties which we identify through which b is 0 implies the imaginary part of z is 0. Indirectly meant part of z is 0, and when a is 0, that means the real part of z is 0. Then we say if for real part of z is 0, z is purely imaginary. If the imaginary part of z is 0 or b is 0, then z is purely real, is how we understand the purely real and purely imaginary complex numbers. Now let's see the square root of a complex number. So finding the square root of a real number is quite easy and understandable, because if I want to find root of 9, it is 3, root of 16 is 4, or if I want to find root of 5, I use the calculator and I can get square root of a 5 or a 3, etc. But in case of the complex numbers, finding the square root is not an easy task, because even a calculator cannot help in finding the square roots of complex numbers. So let's see with various mathematical methods through which we can understand the square root of a complex number. So let's take an example problem where I want to find the square root of minus 5 plus 12i is the question out here. Now how do I find the square root of this complex number is the biggest question here. So in case of such problems where I had to find the square root, I always take this as, let z equals, I take this as x plus iy. Always when I want to find the square root, this is my most common step, that I take the square root of a complex number as some x plus y. Then obviously this will be xy belongs to real numbers, is how we understand. So that implies, now that the root of minus 5 plus 12i is x plus iy, that implies squaring on both sides, I get minus 5 plus 12i under root whole square is equal to x plus iy whole square, because I'm squaring on both sides of the equation. Now when I square the square root, I get root x whole square is x. Therefore, root of a number is the number itself. That implies minus 5 plus 12i will be equal to x plus iy whole square. That is a square plus b square times I square plus 2i xy, using the formula a square plus b square plus 2ab. So that implies I get this to be x square, I square being minus 1, I get this as minus y square as real part plus 2xy times of I, that is minus 5 plus 12i, is what I get as equation 1. Now since these two complex numbers are equal, their real and imaginary parts must be equal. That implies the real parts, which are this and this, and the imaginary parts, which are this and this, must be equal for two complex numbers. So the real part on the left hand side is x squared minus y squared must be equal to the real part on the right hand side, which is minus 5, and my imaginary part on the left hand side is 2xy, and here it is 12, which are equal on the both sides, which I take as equation 2 from this. Now I have found this and this from the two complex numbers being equal. So now the task comes on finding x and y independently. So let's see how we can find x and y using the above properties. Now as I come here, I have my x squared minus y squared equal to minus 5 and 2xy equal to 12, and there are two unknowns x and y and two equations. That is, it is possible to solve these two equations if I substitute one over the other. So let's see how we can solve this in the continued session. Now let's see how we can find x and y. Now as we know that we have the formula a minus b whole square is a plus b whole square, or a plus b whole square is a minus b whole square plus 4ab is how we can write, because when I expand this again I get back a plus b whole square. So using this formula, let's see how we can find. That is, when I wanted to find x squared plus y squared whole square, where a is x squared and b is y squared, then let's see how I can obtain this. With this can be expanded as x squared minus y squared whole square plus 4x squared y squared. Replacing a with x squared and b with y squared, this formula reduces to this. And the intention behind using this formula is that in place of this I can substitute minus 5, which I have for this. So let's see how this reduces. Now x squared minus y squared equal to minus 5 implies minus 5 whole square plus 4x squared y squared, which can be written as 2xy whole square is 12 squared, which is 144. Therefore 4x squared y squared can be substituted for 144, which comes in place of 4x squared y squared. Now this is nothing but 25 plus 144, which is 169. So on the whole, I find that x squared plus y squared whole square is 169, so that my x squared plus y squared is equal to plus or minus root 169. Now it's very important to remember here that x squared is y is equal to y implies x is not root y, but it is plus or minus root y. It is one of the most important formula which the students need to learn. So x squared equal to y implies x is plus or minus root y. It's not y, root y, but plus or minus, which comes here. Therefore, using this, I get x squared plus y squared is plus or minus 13 is what we get. Now this is equation 3. Now from equation 2, I already have this and this. Therefore, let's see how we can get the values. Now initially, if I take x squared plus y squared equal to 13 and see what happens with the equation this, then from here I have x squared minus y squared is minus 5. Then in this case of first case of taking plus 13, I can add so that this gets simplified with 2x squared is 13 minus 5, 8, because when adding this gets cancelled, and therefore I get x squared is 4. That implies x is plus or minus 2, which I get here. Similarly, in case 2, or in this case, when x is plus or minus 2, my y is nothing but 12 by 2x, because 2xy is 12, so y is 12 by 2x, which I get as 12 by 2 times of x. This is plus or minus 2. So on the whole, this is plus or minus 3. That implies x is plus or minus 2 and y is plus or minus 3. That implies my z is x plus iy, in this case plus or minus 2 plus or minus 3i. Therefore, my z is plus or minus 2 plus 3i, which I obtain as the square root of. Now let's take the case 2 of minus 13 and see if this is possible. Now when I take the second case of minus 13, I think this is not possible, because for all x and y belonging to real numbers, x squared plus y squared is always positive. It cannot be negative. Therefore, x squared plus y squared being positive cannot be equal to minus 13. Therefore, as observed from the first and second case, I finally conclude that the square root of minus 5 plus 12i is plus or minus 2 plus 3i is what I get, 1 plus and 1 minus, because of the property which says this. So the square root of a complex number as found using this method for any problem where the square root of a complex number is asked in examination. The method is this. The next is nth root, because we have seen the square root, and then next is cube root or the nth root, which basically comes into existence. So now that we have discussed about square root of a complex number and its method of solving or finding the square root of complex number using the previous method of the session, we'll see how the nth root of a complex number is equally defined. Say for example, if n is a positive integer and say z is a complex number, then there exists w belonging to complex number such that w power n is z. That implies if w power n is z, then w is said to be z power 1 by n is called the nth root. The nth root of z in C. So when I want to find the nth root of this, I just find this of z in C. That is, if suppose I wanted to take the previous example, if I wanted to find the square root of minus 5 plus 12i as taken in the previous session, that implies my w, I take it as, if I take my z as minus 5 plus 12i, then in that case w is equal to root z, or w is z power 1 by 2 is how I understand this with the square root. The concept of w equal to root z is understood as z power 1 by 2 in this concept, or this can also be understood as w square equal to z, which is w power n equal to z, is how we get the nth roots understood in the form of this formula. W is z power 1 by n is the nth root of z, is the conclusion. So therefore, when I have z power 1 by n is called the nth root of z in C, is the most simple way of understanding the nth root of a complex number. Z power 1 by n is the nth root of z in C. So modulus of a complex number, which is also called the absolute value. Let's see what is modulus or absolute value of a complex number. Say for example, I take a complex number z equals a plus ib belonging to the set of complex numbers. Then the modulus of z denoted by this is called modulus of z, which is denoted by mod of z is nothing but mod a plus ib, that is root a square plus b square. So we define the mod z as root of a square plus b square, where z is a plus ib. Now, as I clearly see this, I understand that this cannot be a negative number. So the note is mod z is always greater than or equal to 0. It cannot be a negative value. And not only that, my second note says that mod z is a real number. That is, this cannot be imaginary, but this is purely real. There is no imaginary part attached because there is no a plus ib out here. Is how we understand the properties of modulus or absolute value of a given number. Say for example, I wanted to find mod z for this. For example, if I have z equals 3 plus 4i, then how do I find modulus of z for this problem? Is that I find mod z using this is a and this is b. So root of a square plus b square, which is root of 9 plus 16, which is 25. That implies root 25 is 5. So mod z is 5. Is how we understand the example through the modulus or absolute value of a complex number. Now that we have defined the modulus, say if I have my z is x comma y, that is x plus iy, that implies modulus of z is defined as root of x square plus y square, the mod z, which is also read as mod z. So this is given by root of x square plus y square. Now how do I understand this geometrically? Say for example, I take a ray OX and a ray OY, along which this is represented with 0, 0, and here is a point P, which is x, y, that is this point x, y, which lies out here. Then the distance from origin, that is 0, 0 to pxy, is called mod z. That is, if I just join from here to here, this distance is called mod z. That is, the distance from here will be root of x square plus y square. And the reason is this unit, this will be x and this will be y. Using the Pythagoras theorem, I get mod z as root of x square plus y square, which is this. And hence, the distance from 0, 0 to pxy will be, by Pythagoras theorem, mod z square is x square plus y square, or this OP square is this. That implies OP is root of x square plus y square. That implies OP, which is defined by mod z, is root of x square plus y square. So geometrically, we conclude that mod z or mod of z is the distance of the point pxy from 0, 0, is how we understand geometrically mod z or mod of z is the distance of the point P from 0, 0, this distance being mod of z geometrically. Now let's see what happens if the magnitude is 0? So we take it as one of the exclusive property. That is, if the first property I take z equals xy belong to C. Now in this case, that implies mod z is mod of x plus iy, that is root of x square plus y square, as we have recently defined. Now in the first property, if I wanted to know what exactly is the condition for magnitude equal to 0, that is when mod z is equal to 0, if and only if mod x plus iy is equal to 0, because z is x plus iy. Now this is if and only if mod f x plus iy is root of x square plus y square equal to 0, and this is if and only if x square plus y square equal to 0 is what we get when I square on both sides. Now this is possible only when each of them is 0, because the sum of squares is 0 is possible and only when both of them are zeros. That is, if and only if x is 0 and y is 0 implies z equal to 0, 0. Therefore, I conclude that mod z is equal to 0 if and only if z equal to 0, 0 is how we understand the magnitude is 0 implies the point P converges with origin, and hence we get z is 0, 0. The 0 complex number is how we understand the mod z equal to 0 implies this. So geometrically we understand that this is geometrically mod z equal to 0 implies distance of pxy from origin is 0, and this is possible only when P converges with 0. That implies pxy is equal to 0, 0. That implies this is how geometrically we understand the concept of the mod z equal to 0. Then the distance of P from origin is 0, then these two converge and they become equal, and hence x and y are zeros, and hence z is 0, 0. The property 1 of modulus. So let's see some properties of modulus connected with conjugate of a complex number. So now that we have discussed about conjugate of complex number, initially the first property has already been discussed, and now the first thing I discuss here is mod of the two complex numbers, or if I take z1 and z2, then mod of z1 into z2 is mod z1 into mod z2 is what we get for the first property. And similarly, if I have mod of z is always equal to mod of z conjugate, that is, for a conjugate and its complex number, the modulus is always same, is how we understand this. The next is, if I multiply a complex number with its conjugate, I get mod z whole square, is how we understand this property. So z times of z conjugate will be mod z whole square. Fourthly, I have mod z1 plus z2 is less than or equal to mod z1 plus mod z2 is how we understand. It is not exactly equal, but at the most less than or equal to this. And next is the mod of real part of z is always less than or equal to mod of alpha. The modulus of real part of z is always less than or equal to modulus of z, or it's not alpha, it is the complex number z taken out here. And next, I have the modulus part of imaginary part of z is nothing but equally less than or equal to modulus of Z. So modulus of the real or imaginary part will always be less than or equal to the modulus of the whole complex number, is how we understand the concept. Next, I have mod of Z1 plus Z2 whole square is mod Z1 square plus mod Z2 square plus 2 times of real of Z1 Z2 conjugate, is how we understand this property. Property number 6. And lastly, I have the 7th property, which says that mod Z1 plus Z2 whole square plus mod Z1 minus Z2 whole square is 2 times of mod Z1 square plus mod Z2 square, is how we understand each of the properties of modulus as connected with the complex numbers. Now this session is about connecting the Cartesian coordinates with polar coordinates. What are Cartesian coordinates and what are polar coordinates is the biggest question out here. So now when I consider the points in the form of Pxy, say the points taken in the form of x, y, where x is the first or x coordinate and y is called the second or y coordinate, is called the Cartesian coordinate involving x and y, x counted along x-axis and y along y-axis. Similarly, there are different types of coordinates in the xy real coordinate system or complex coordinate system. Now, the polar coordinates are one of the types of coordinates which are existing in maths. So when we have Cartesian coordinates as xy, let's see how the polar coordinates are defined for these Cartesian coordinates. So for a fixed point Pxy in a plane, I take here a fixed ray x dash, which is called the initial line. I call this as initial line, and of course it is a ray which I take as initial ray. Now x dash is the initial ray, is the initial ray. Now for this initial ray, I also take the initial the next ray, which is y dash. For this, my initial point here is 0, 0, which I take here. This is called my initial point. So with this initial point, let me see how the polar coordinates are defined for this point Pxy. Now let me say the point Pxy is somewhere out here. That is Px, y is a coordinate here. That implies that if I drop a perpendicular here, I get this to be x and this as y, because P is x units from here and y units away here. So this is x and this is y. Now let me take this as r, the distance OP. I denote this with O, and let me take the distance OP as some r, is how I understand this. Now for this, let me say the angle made by OP with the initial line x dash in the anti-clockwise direction is theta. So this is r and this is theta, which I define. So here OP, that is the distance of point Pxy from initial point, this is taken as r, that is r. So the distance of point P from initial point, this is r, and then my theta is the angle made by OP with the initial line in anti-clockwise direction. The direction is very important here, or else we assume the angle to be from here to here. So angle made by OP with the initial line x dash in anti-clockwise direction. Now from this, if I take OP and if I take this as A, then OAP is a right angle triangle where I can use Pythagoras theorem. Therefore, by Pythagoras theorem in triangle OAP, OP square is AO square plus AP square, but my OP square is R square, which is AO, and this being x square plus y square. That implies my R is root of x square plus y square, and therefore this is mod of x plus iy, because by definition of modulus I get this as by definition of modulus, but this is nothing but mod z, because if I take z as x plus iy such that z is equal to x plus iy belongs to C, then my R is mod z. So R is modulus of z, which I have defined here. Now the coordinates which I generally represent, for each of theta there is an R, that is, for infinitely many points on R there are different angles of theta which we consider. Therefore also R ranges from 0 to infinity, because there are infinitely many points which are possible, so different regions give different R values. Ranges from 0 to infinity, since P is any point on the plane, and hence there are infinitely many points for which R ranges from 0 to infinity. And not only that, theta ranges from 0 to 2 pi, because it goes at the most from 0 and ends at 2 pi, one full circular revolution or rotation. Theta ranges from 0 to 2 pi is how we understand. To continue with the session. Now here comes the question on what are polar coordinates and what are Cartesian coordinates. Now as I take here, I clearly see that if the point P is here, it is x units from origin and y units from x y axis and y units from x axis, that is in the form of x units away from origin here and y units away here. So in this case we see that every point which lies on the plane, there will be different values of R and different values of theta. That is, for every point which changes, suppose my point P changes somewhere out here as P x1 x dash y dash, then my new R will be this and my new angle will be theta dash. So in this way different points lead to different changes of R dash and theta dash. Therefore I understand that as Pxy changes on the plane, R theta also changes correspondingly. That is, both R and theta change because the position of the points change, the value of R and the angle also changes correspondingly. Therefore, R theta are called the polar coordinates of the respective point Pxy for all xy belonging to R is how we understand the difference between the polar coordinates and the Cartesian coordinates. That is, if P, X, Y are the Cartesian coordinates, then its polar coordinates are given by R theta, R being the distance from origin to P and theta being the angle made by the line with the initial line x, x dash in the anti-clockwise direction. So R theta are called the polar coordinates of the respective points P, X, Y for all x, y belonging to R. The polar coordinates are R and theta, where R is the distance and theta is the angle. Now let's see how the polar coordinates can be represented in trigonometric form. They have been connected with angles with trigonometric ratios sin theta, cos theta. So let's see how the sin theta and cos theta are connected with R and theta, that is the polar coordinates. Now as we see that if z is x plus iy, that is xy is a complex number, I find that x and y are real numbers. Therefore, my point P xy is called polar representation, is called the Cartesian representation of P, of point P. Now, similarly, if I represent this in the form r theta, this is called polar representation of point P, where r and theta are the polar coordinates. So r and theta are independently called the polar coordinates, and the point represented in the form r theta is called polar representation of point P. Now let's see how this polar representation is connected with the trigonometric form is what we are going to see. So let's revisit the diagram which we have taken in the previous session. So let's take the initial line as taken in the previous case of this is x, x dash, and this is y, y dash, through which I take a Cartesian coordinate or Cartesian representation of point P, x comma y, which I take somewhere here. Then we have observed that this point is initial point 0 comma 0, and this is the initial line x, x dash. So O is 0 comma 0 and P is x comma y, so that when I drop a perpendicular, I get this as x and this as y. And of course, this was r, which we have already discussed as in the polar coordinates. So r is this, and theta is the angle in the anti-clockwise direction, which is this. So taking this as A. Now as we have seen this diagram already, let's see how we can use this in connecting the polar coordinates with the trigonometric form. So clearly, when I see here in triangle OAP, it is a right angle triangle. Therefore, I have sin theta, which I'm going to have as sin theta is opposite by adjacent, that is opposite by hypotenuse, which is nothing but opposite side is AP and hypotenuse, which is OP. That implies my sin theta is AP, which is y, and my OP, which is r. That implies when I cross multiply this using AP and OP, I get this to be y equals r sin theta, which I take as equation 1. Similarly, when I take cos theta, it is nothing but adjacent by hypotenuse, which I get from adjacent, which is OA by OP. Therefore, this on substitution gives me OA, which is x, and OP, which is r, which on cross multiplication gives me x equals r cos theta, which I take as equation 2. So I have obtained the values of x and y in terms of r and theta, which are the polar coordinates. So the Cartesian coordinates are connected with the polar coordinates as x equals r cos theta and y equals r sin theta. Let's see how the polar representation is done in trigonometric form, to be continued. Now let's take the two equations from which I got x equals r cos theta and y equals r sin theta is what is obtained from each of the cases. Now with this, we know that we have z is a complex number which belongs to C, implies z equals x plus iy. That is, in the form of iy, x is substituted for r cos theta and y for r sin theta, so that I get x is r cos theta as substituted from equation 1 plus I times of y, which is r sin theta as substituted from this, since from 1 and 2, the two equations. That implies z is, taking r common, I get cos theta plus I sin theta is what is called the polar representation in trigonometric form. Polar representation of z in trigonometric form, which includes cos theta and sin theta. So when I represent this in trigonometric form, I write z as r times cos theta plus I sin theta, where my r is root of x square plus y square, that is mod z, which we have recently seen in the session using Pythagoras Theorem. Now we'll see how the Cartesian coordinates are expressed in polar coordinates form, that is, how we can express r and theta in terms of x and y. X and y are the Cartesian coordinates of P, and r and theta are the polar coordinates of the point P. So let's see how r and theta can be expressed in x and y. Now we have already seen for r that using Pythagoras theorem, initially by Pythagoras theorem, I have r square is x square plus y square, because clearly I can see the Pythagoras theorem which says r square is this, that is, r is root of x square plus y square, is how I express r in terms of x and y. Similarly, let's see how theta can be expressed in x and y. So in triangle OAP, I see that I have tan theta, which is opposite by adjacent, that is, opposite side is y and adjacent side is x, is what I get for this theta. Opposite is this and my adjacent is x. That implies tan theta is y over x. That implies theta is tan, when it comes to the right, comes as tan inverse of y over x. This is how I get the theta in terms of x and y and r in terms of x and y, which are the exclusive formulas, because when the Cartesian coordinates are given, we have to convert them into polar coordinates by just substituting x and y in each of these cases. Now, therefore, we have r is equal to root x square plus y square, and at the most this can be greater than or equal to 0. Therefore, the domain of r is, and theta, which can range from 0 to 2 pi, covering all the 4 quadrants, has its domain which lies between 0 and 2 pi, is how we understand the range of r and theta and the coordinates r and theta as converted from Cartesian coordinates. Now that we already know what is z and what is r, let's see how they are related with each other. As each of r and theta are related with x and y, let's see how r is related with z. Now in this case, we have z is x plus iy or x comma y in the way that I can represent z as x plus iy, or this is mod z. Let us consider the modulus of z and see what happens when modulus of z is expanded for. So when z is x plus iy, if I consider mod z, we know that mod z is root of x square plus y square by definition of modulus. This is by definition that I get this. Now we know that x is r cos theta, which we have derived from the triangle x is r cos theta and y is r sin theta as obtained in the previous equations. Let's substitute in place of x as r cos theta whole square and in place of y as r sin theta whole square. So on further expansion, I get r square cos square plus r square sin square, which on taking common with r square, I get sin square plus cos square if I arrange these two in order. Now we know that sin square theta plus cos square theta is always 1, which we have as a formula in the trigonometric ratios. Therefore this equal to 1 implies I get this to be root of r square times 1, this being equal to 1. And therefore this is root r square, which is r, since r is greater than or equal to 0, or else this would have been plus or minus r, but this is r. And finally we see that r is mod z is how I understand the relation between r and z. So r is equal to modulus of or absolute value of the complex number z, which is x plus iy. Now let's see what is meant by amplitude of a complex number. So if I take a complex number z equals x comma y, that is x plus iy belonging to C, that implies I have x and y belongs to real numbers, is how I understand. Now as I connect this with the polar coordinates, I see that clearly if P is a point, then I have the origin with point xy, and this is r, and this is x, and this is y, is how they are connected, as can be seen. X, y, y dash is how we get. Now when I see the point P, which is related with the complex number x plus iy, we have to define amplitude. For this, let me consider the triangle where this is theta in the anti-clockwise direction and this is A. So we have in triangle OAP, sin theta is opposite by hypotenuse, that is y by r, which we have already discussed. Opposite by hypotenuse is y by r. That implies sin theta is y by r, which is y by root x square plus y square, because by Pythagoras theorem we have already seen r is root x square plus y square. So r can be substituted with this, which is sin theta. Let me take this as equation 1. Now similarly, when I take cos theta, let's see what happens with the relation. Now cos theta is clearly adjacent by hypotenuse, so this clearly is x by r. That implies I get my cos theta is x by r, which is x by root of x square plus y square. Is what I get from equation 1 and 2. Now the amplitude of z is defined as the value of theta which satisfies both the equations 1 and 2. So here we define the real number theta which belongs to R is called the amplitude of Z or argument of Z if it satisfies equation 1 and 2. That means the value of theta which satisfies both equation 1 and 2 is called the amplitude. So real number theta is called amplitude of Z if it satisfies both the equations 1 and 2. And note, theta we know always belongs to 0 to 2 pi is how we understand. So now that we have defined amplitude or argument of Z as that angle theta which satisfies both equation 1 and 2, now next comes on what is principal amplitude or principal argument. The word principal means first or the very first. So therefore we say that the first angle which satisfies both equation 1 and 2 is called a principal amplitude or a principal argument. Now this is very much associated with mathematical property that there exists at least one angle which ranges from minus pi to pi for which the theta satisfies equation 1 and 2. There might be another angle which lies in this region and which satisfies the two equations, equation 1 and equation 2. But the first angle which lies from pi to minus pi lying in this region is called the principal amplitude because that is the first angle which satisfies equation 1 and 2. The second angle may satisfy in these two regions, the third and fourth quadrant, but there is at least one angle in the first or second quadrant which satisfies equation 1 and 2, and that angle by definition is called principal amplitude or principal argument of Z. Now we define the principal amplitude as the value of theta which belongs to real numbers which lies in the region minus pi to pi, that is in the first and second quadrant, and satisfies equation 1 and 2 which we have discussed in the previous session. So it is denoted by argz. So the principal amplitude is denoted by argz and is nothing but theta, which is given by the formula tan inverse of y by x, where x is not equal to 0 is how we define the principal amplitude or the principal argument of Z denoted by argz is equal to theta is this how we define in the case. So when any problem is given, it is about just substituting the values of x and y, the real and the imaginary part, and then simplifying accordingly. So now from trigonometry, let's derive the properties which we have derived in the trigonometry. Let's consider the properties of trigonometry. As we know that since 2n pi plus theta of sine is sine theta, then that implies if theta is the amplitude. Now that we have discussed about polar coordinates converted from Cartesian coordinates, we will see what is meant by polar form or modulus amplitude form. So the complex number z equals x plus iy belonging to C implies x comma y belong to R. That is, let z equal to x plus iy, which belongs to complex numbers, then x and y belong to R. Now correspondingly for this z, we have seen that there is a point pxy which is related with its polar coordinates r and theta, as we have seen, such that r is given by the formula cos theta plus I sin theta. So this is called the polar representation of z, or this is called the polar form of writing a complex number, where I have theta lying in the region minus pi to pi including. So between minus pi and pi is how we understand the polar coordinates. Now this is called polar form or modulus form of representing a complex number. So this is one of the way of representing a complex number called the polar form, cos theta plus r sin theta. So generally we don't write the complete sentence, but sometimes this is written as cos theta plus I sin theta is generally written in the short form as cis theta. That is, cis theta implies cos plus I sin, which is directly written as cis theta. So let's find the various properties of cis theta, that is the polar form of representation of the complex number z. So z in its Cartesian form or in the complex form is given by the polar form as r equal to cis theta, which has various properties which we're going to identify now. So reconsidering here, I have r equals cos theta plus I sin theta because cis theta is cos theta. So therefore, replacing theta by minus theta, I get r of cos minus theta plus I sin minus theta. Therefore, if I further simplify this, I know that cos of minus x is cos x and sine of minus x is minus sine x, which are the two basic formulae in trigonometry which I'm going to use here. Now cos of minus theta is cos theta, so I get this as cos theta minus I sin theta because sine of minus theta is minus sine theta. That implies r is cos theta minus I sin theta. So in this case, I see that there are some relations out here through which I want to derive. Now what I do is I consider 1 times of 2, that is the product of 1 and 2, which is nothing but cos theta plus I sin theta, which is equation 1, times cos theta minus I sin theta, which is the relation of the product 2. Now this on simplification gives me a plus b into a minus b, which is a squared minus b squared, which I get using the formula is a plus b times a minus b. Now this on further simplification gives cos square theta minus of I squared, which is minus 1, because we know that I squared is minus 1. So I get this as minus 1 times sine squared, which on simplification gives cos square theta plus sine square theta, because minus of minus is plus, which is nothing but 1. And therefore I observe here that my cos theta plus I sin theta times cos theta minus I sin theta equal to 1 implies this equals 1 by this. That is, cos theta plus I sin theta is 1 by cos theta, or this is 1 by cos theta plus I sin theta. So I bring the plus sign down. So in this case, my cos theta minus I sin theta, which is cos of minus theta plus r of sine minus theta, that is cis of minus theta, because I can write this as cis of minus theta, because replacing theta with minus, I get cis of minus theta as cos theta minus I sin theta, which is cis of minus theta. Therefore, I have cos theta minus I sin theta is cis of minus theta, that is 1 by cos theta plus I sin theta, which is cis theta. Therefore, I derive here that cis of minus theta will always be 1 by cis theta, is what we have derived out here, is what we get when we derive the proof of cis of minus theta is 1 by cis theta. So let's see other properties of cis theta connected with the mathematical formula. So let's take all the properties of cis theta as listed out here. With the first one, that cis of minus theta is 1 by cis theta, and secondly, cis power m theta is cis m theta is how we get here. Now here I have cis power m theta is cis m theta, and my next formula is if I multiply cis theta 1 times cis theta 2, then this would be cis theta 1 plus theta 2. And fourthly, if I divide cis theta 1 with cis theta 2, I get this to be cis theta 1 minus theta 2. Then fourthly, fifth property is that if I just replace theta with pi by 2 minus theta, it is just like sin 90 minus theta is sin theta, cos theta, and cos 90 minus theta is sin theta. Cis pi by 2 minus theta is cis theta is how we understand the properties. So the many properties which connect cis theta, and these are the basic properties. And there's another property which says that cis theta is e power I theta, which we learn in future classes. It is very important, but we learn this in the next sessions about how the exponential and cis are connected with each other. So now that we have discussed about the various properties of cis theta or the polar form with its varied properties, let's see the properties of the argument of Z, that is the principal amplitude of the complex number Z. So with the properties, the first property of argument is that argument of Z1 times Z2 is given by argument Z1 plus argument Z2 plus n pi for some n belonging to -1, 0 and 1 is how we take the first property. Secondly, we see that if I take argument of Z1 over Z2, then this is argument of Z1 minus argument of Z2 plus n pi for some n belonging to -1, 0, 1 is how we understand the properties of argument or the principal amplitude of Z. Now let's see various properties of cis theta, that is some of the standard values of cis theta. Now as we come with cis theta is defined as cos theta plus I sin theta. The complex number cos plus I sin is denoted by cis theta. Therefore, what happens when I put theta equal to 0? Initially, I want to put theta equal to 0. Then in this case, I get cis 0, which is cos 0 plus I sin 0. Now cos 0 is 1 plus I times of sin 0 is 0, which gives me the answer as 1, because 1 plus 0 is 1. That implies I have the property that cis 0 degrees is always 1, is how I understand this concept. Now similarly, when I put theta as 90 degrees, let's see what I would be getting for cis pi by 2. So now that cis 0 is 1, proceeding in the similar manner, when I take theta equal to pi by 2, my cis pi by 2, which I need to find for theta, I get on the right hand side as cos pi by 2 plus I sin pi by 2, which is nothing but cos 90 we all know is 0 plus I sin 90 we know is 1. So using the values of cos 90 and sin 90 and substituting here, we get 0 plus I into 1, which is 0 plus I, which is nothing but I, the complex number I. So I understand that cis pi by 2 is the complex number I. So in this manner we can find cis of various values which we need to find here. So for example, if I wanted to find cis minus pi by 2, then How do I find sys minus pi by 2? That is, when I take sys minus theta, we all know is 1 by sys theta, that is cos theta minus I sin theta. So this is how we get for sys minus theta. Therefore, theta equal to pi by 2 implies I get sys minus pi by 2, which I wanted to find as cos pi by 2 minus I sin pi by 2, which on simplification here on the right side gives me 0 minus I times 1, because sin 90 is 1 and cos 90 is this. That implies I get this as minus I, because 0 minus I is minus I. Therefore, I get sys of minus pi by 2 is minus I, which I identify as the different properties which we get here. Similarly, when I take theta equal to pi, that implies sys pi would be cos pi plus I sin pi, where in this case cos pi is minus 1 and I times of sin pi is 0, which is nothing but minus 1. Therefore, sys pi is minus 1. So these are the 4 basic standard values of sys theta, which we have to know them as standard formulae. One is sys 0 is 1, sys 90 is I, sys minus pi by 2 is minus I, and sys pi is minus 1. This is how we understand the various properties of sys theta and sys minus theta. So now the next topic comes on geometrical representation of a complex number. Now here, one of the famous mathematician called Gauss has come out with an idea of representing the complex numbers on a plane. As we represent the points on a real xy coordinate system, similarly Gauss has attempted, he was the first mathematician to have attempted on writing the complex numbers in a plane, or just putting the points represented by complex numbers on a plane. So according to his method, we will see how the points can be represented on a plane and how the process of geometrical representation can be done for a complex number. So when we take the complex number z equals this or this belonging to C, that implies xy belongs to R, then in this case every complex number a plus ib is written in the form a comma b, or x plus iy is written in the form x comma y. That implies the representation of a complex number in the form of x comma y implies x, which is real part of z. Basically we know that this is real part of z, which is real part of z is represented as an x coordinate in the plane. So we represent this as the x coordinate in the plane, and my y, which is imaginary part of z, is represented as a y coordinate in the plane. So this is how I differentiate between representation by an x coordinate and by a y coordinate respectively in the plane. So I take a plane with 2 perpendicular axes out here. That is, when I take the 2 perpendicular axes in this form, then from here, when I want to represent this as a point P equals x comma y, which is indirectly the representation of a complex number z, then I try to take this in the point form, that is x plus iy is taken as x comma y, where the real part of x is the x coordinate and the imaginary part of z is the y coordinate. Therefore, I get a point P which is x comma y, and which is x units from x-axis and y units from x-axis here. So this is x units from origin along x-axis, and this is y units from origin along y-axis, and that is how the point P is obtained. And of course, this is 0, 0, which is noted by O, is how we represent the complex number. So remember, the complex numbers are generally denoted by a vector form, denoted by the complex number Z is denoted by a vector. In this case, the vector is OP. So we always try to represent the complex numbers in the vector form or OP form. So this kind of representation of a complex number in the form of Pxy in the plane is called Argan plane. The plane on which I use the complex number coordinates in representation here is called, this entirely is called Argan plane. It's not a real xy coordinate system, but it is an Argan plane because the complex numbers are taken in the coordinates form to be represented. Say for example, I wanted to represent the complex number -3 minus 2i. So indirectly I write this in the coordinate form -3 minus 2, where the real part is x coordinate and imaginary part is y coordinate. Then when I plot this, I get -3 minus 2, somewhere 3 units left and 2 units down. So here I get some q which is -3 minus 2, and this represents the complex number. OQ, which is out here, in this case OQ represents vector OQ represents the complex number Z equals -3 minus 2y is how I understand in this Argan diagram. So in this Argan diagram, I have represented this with a point Q, with x coordinate being the real part and the y coordinate being the imaginary part, and this is plotted on the Argan diagram, which has two perpendicular axes, and then -3 is 3 units to the left and -2 is 2 units down, and I get a point Q. When I join with origin, I get OQ, the vector OQ, which represents the complex number Z equals -3 minus 2i. So like this, every complex number can be represented on this plane using the concept of x and y coordinates, is how we understand the concept. Now comes the special case of identifying the points on initial and vertical line. So let's take the Argan plane where I represent the complex number Z equal to x plus iy. So let me take the Argan plane out here. X dash and y dash, and the complex number Z equal to x plus iy is represented on the Argan plane with P equals xy. But here, if suppose I have a complex number 3i or Z equal to 3i, then in that case, what will be its respective coordinate? Because I can write this as 0 plus 3i. In this case, my real part is 0, that is, my x coordinate is always 0. That means when my x coordinate is 0, all the points on y-axis are purely imaginary, is how I understand. Similarly, when I take Z is equal to 5, it is a complex number. If I write this in the form 5 plus I times of 0, then in this case, this is a complex number which is represented by real part is x coordinate and imaginary part is y coordinate. So 5, 0 So when I write a complex number which is purely real, then that point, its respective point, lies on x dash. That is the horizontal axis or initial line. And when I take the complex number which is purely imaginary, that respective point lies on the vertical line, that is y dash. So here that if a complex number is purely real, then its vector lies along the initial line, that is the horizontal line x dash, is how we understand the property. That is, that point purely on this x dash, the complex numbers are purely real, and on this y dash, the complex numbers are purely imaginary, is how we understand. Now, with the second property says that if a complex number is purely imaginary, then its vector or its corresponding vector lies along the vertical line, that is the ray y dash. Therefore, every point on this will be purely imaginary and every point on this will be purely real, are the two special cases which need to be identified through these examples. Now that we have represented the complex numbers as vectors on Argan plane, we will try to understand the geometrical relation between a complex number and its conjugate, that is z bar. So how is the relation between a complex number and its conjugate understood in the geometrical sense, is what we are going to discuss in the session. Say, for example, I take a complex number z equals x plus iy belonging to C, then that implies its conjugate, which is z bar, that is conjugate of z denoted by z bar, we all know is x minus iy, because conjugate is obtained when I replace I with minus I. This also equally belong to C for x and y belonging to R. Now that the conjugate is with this and its respective complex number is this, let's represent them on the Argan plane. Now when I want to represent complex numbers in the Argan plane, the first thing I do is identify the points which are connected with the complex number. So to start with z, let me take the point P, that is x plus iy. The real part is x and the imaginary part is y. So here is the point P, which represents the which is represented using the Argan plane. Now for this point z conjugate, here I have Q, which is represented with this as real part and imaginary part. Now I'll be plotting these 2 points in an Argan plane, where P corresponds to z and Q corresponds to z bar. So therefore, if I take the Argan plane with initial line x dash and with y dash, then in this case my point xy is initially plotted here from origin, which is 0, 0, and x, y, say my P is out here. Then in that case OP represents the complex number z, because OP is connected with x, y. Now let me plot x minus y out here. That is, I go x units here and equally minus y here. Therefore, my q is x minus y. So this represents z and this represents the conjugate of z. So when I see these two, I understand that the conjugate of z is exactly the mirror image of this with respect to the ray x dash. So my geometrical relation between z and z bar concludes from the Argan plane that OQ vector OQ is mirror image of vector OP with respect to the initial line x dash. That is, if I take this as the mirror, then this is mirror image of this and this is mirror image of this. Therefore, I conclude that z and z bar are mirror images of each other with respect to the initial line x dash. So this is the conclusion made out here. So the conclusion is that the relation between z and z conjugate is that z and z conjugate are always mirror images of each other with respect to the initial line x dash. So they will always be mirror images with respect to the x-axis or the initial line x dash. This is how we understand the relation between z and z conjugate. Now let's see some properties of conjugate of a complex number continued from the previous session. Now, as we take two complex numbers, there are various properties which come under conjugate of a complex number. So when I say I want to find the conjugate of the complex numbers z1 and z2 together, then it is conjugate of each of them. That is, conjugate of the sum is sum of the conjugates. Now secondly, if I have the product or difference also is the same. If I have the product, z1 times z2 conjugate is z1 conjugate times z2 conjugate. And thirdly, if I have z2 is not equal to 0, that implies z1 by z2 conjugate is each of the conjugates which I get. Conjugate of z1 by conjugate of z2, provided z2 is not a zero complex number. Now this is conjugate of conjugate, that is, conjugate of z of whole conjugate is nothing but again this. This is because since I take, for example, x plus iy, then its conjugate is x minus iy, and again I replace the conjugate. If I want to find conjugate of this, then I replace I with minus I get back z. So that implies z conjugate whole conjugate is again x plus iy, which is z, is how we understand conjugate of z of whole conjugate is again the same complex number. So these are the various properties through which we try to solve various problems connected with conjugate of a complex number.